All right, Math 5130. This video I will demonstrate how to present the results of a logistic regression analysis. I'm not going to include the descriptive section, but that would need to be included. And you can look at the two-way ANOVA write-up from lesson 5. That would work pretty okay as a template. But after the box plots and histograms, you'd go into this narrative. You'd also want to make sure that you reported the means and standard deviations for all of the quantitative predictors over false status. So, for example, for upgo, you would want the mean and standard deviation upgo for those who fell, and the mean and standard deviation for upgo for those who did not fall. But I've demonstrated that previously. In an effort to save time, what I've done is I have the R script already up, and I'm just going to run through this. You will have this. I saved it, and we'll share it with you on Blackboard. So the first thing we do is just identify the problem, tell the reader what we're going to do, and we're going to perform a regression, direct logistic regression analysis on false status with 4 predictors. Next thing, I report the sample size, which I've done with length, and then we dive into the percentage of patients who reported a fall versus those who did not report a fall. And you'll notice what I did over here because of kind of the caveats in R. All of my categorical variables that are included, I need to force them as a categorical variable. And so I did, I did falls up here, and then I did the same thing with steady AM down here. Well, actually right there. So again, the purpose is this line. I force false status, and I retype it as just lowercase false, because that's easier to type. And the next thing I do is I establish my reference category, since I have going to create dummy variables. And then I get into my counts and percentages right there, which I've reported over here in the first paragraph. Same thing, I go ahead, force steady as a factor, and then relevel where I have the appropriate reference category. Then I call the model, and then I look at the summary. So we'll get into this kind of later. Now, here's the probably the hardest thing that goes on. The rest of it you'll see is just really reporting from the summary of the model. But this paragraph is a little confusing, so let me explain. The first thing we do is we dive into the model diagnostic, and we determine whether the model is statistically reliable. In other words, is this model better for predicting false status than just flipping a coin? And the way you do that is you compare the null deviance with the residual deviance. So you can see that I made that subtraction right there. So that subtraction is 10.98. It turns out that this follows the chi-square distribution, so I calculate the p-value this way. And notice I just put in the 10.98 and then the 243 minus 239, which is the difference in the degrees of freedom. Now, if I were doing this problem, I would just in my head see that the difference in degrees of freedom is 4, and I would just type a 4 there. But I'm teaching, not just doing. So this gives me my p-value, which I have reported right here, is less than 0.05. The next thing I do is I compare the AIC. So the AIC for the full model was 330.01. And then I run the null model using this command. I predict falls from the constant 1. And I can see that the AIC there is 332.99. When the AIC is lower, that indicates a better fit. So I report that there. So the AIC for the full model is 330.01. It's lower than the constant only model, indicating a slightly better fit. Now, we talked about in the previous video prediction accuracy using PAC, the percentage of accurately classified cases. Sorry, I'm on my first cup of coffee. And so where are we? So this sentence right here is what I do from here to here. So let's talk about that. So I'm creating my confusion matrix, which again I've devoted an entire instructional video on that. Fortunately for you, you'll have this script. If you name your model, then all you have to do is just copy and paste this exactly. And again, your data set has to be called data. The next thing you can do is just type the expected exactly like that. This sets the threshold at 0.5, which is the industry standard. So you don't have to do anything really other than copy and paste this line into your code. The next thing you would type is table expected, whatever your dependent variable is named. Remember, I named mine false. Then it'll give you the confusion matrix. So remember, the sensitivity is the percentage that were of the positives that were accurately classified. So that would be 25 divided by 25 plus 76. And then specificity is the percentage that weren't, that false didn't happen. What percentage of those were accurately classified by our model. So it'll be 125 divided by 125 plus 18. The percentage of accurately classified cases are the sum of these two boxes, the true positives, the true negatives, divided by the total sample size. So you can see that the sensitivity, the specificity, the PAC are all reported in this, well, that one sentence, actually. And specificity, 87.4% is impressive, acceptable. 24.8 on sensitivity is quite low. But that's a good point. Remember, you don't need to go into a lot of interpretations here, because think about who your audience is. It's people in your field who should have some background in statistics. The next thing I do is I dive into the regression coefficients, and I go back to this. Let me find it. Okay, I go back to this model to get all that information. All right, so I can look through here and I see that only feel and age emerged statistically significant. So I say that according to the Wald criterion, age and feel reliably predicted false status. The odds ratio, which you can easily find from, where is that? Yeah, right here. The odds ratio, which is just taking each coefficient, or times, I'm sorry, taking E and raise it to the value of each coefficient. Those are easily found right there. So I report the odds ratio for the two variables that are statistically significant, and neither one are super impressive because they're relatively close to 1. Next thing I do is I dive into the variance inflation factors. We've done that previously. You can see that you have to load the package car to be able to run these. Remember, the cutoff for the VIFs is 5. So as long as none of your VIFs are 5 or larger, then we're not worried about multicollinearity being a problem. The next thing you get into, it's kind of weird, but we're just testing one of the major assumptions. There really aren't a lot of assumptions for logistic regression. We don't have normality, we don't have the other stuff, but we do need to test the linearity assumption. And it's kind of strange the way that we do this. So the first thing we do is we create variables. Okay, let me pump the brakes here. This is a source of confusion for my students sometimes. The linearity assumption applies only, okay, I did write that right there, to quantitative predictors. If you try to put one of your categorical predictors in here, you're going to get an error because you don't do that. You only choose the quantitative predictors. And in my case, I have three of those. I have H, the up-go test result, and the feeling score. So I only need to create these new variables based on the three quantitative predictors. And you do that by creating a new variable, which is I call just log age. And I create that by taking literally the logarithm of age times itself. So the log of age times age. I create log of feel. I take the log of feel times itself. Log up-go, take the log of up-go times itself. Now, what I do is I keep my model as I had it before, keeping all variables, including the categorical variables, but then I add these three right here that I just created. Once I create this model, I have tunnel vision on these three values only. I don't care about anything else in the model. I have excuse me, I have tunnel vision on log age, log feel, log up-go. If any of those are statistically significant, you must delete that predictor from your model. So you can see that log age is not significant at the 0.05 level, log feel is not significant, and log up-go is not significant, so I feel comfortable proceeding keeping age, feel, and up-go in my model. The next thing I get into is the logistic regression table, and a lot of that's going to be just directly taken from, okay, now ignore this table from now on. We go back to the model that I created up here. And it's just transferring the information over here, the beta, which is the estimate, the walled statistic, which is the z-value, the p-value, which is the p-value, and then the odds ratios, which I reported right down here. Now, the confidence intervals for the, let's see, where did I do those? Yeah, right here. The confidence intervals, you can see that I forgot how to do it. The confidence intervals that I reported here, for example, age is 0.93 to 0.999. I got that from this command right here. So again, as long as you name your model, these commands are pretty simple to do. So the next thing I do is I dive into the effect sizes, and the effect size, the area under the curve for a receiver operating characteristic graph is the effect size that I typically report. There are others, but I think this is the easiest to grab, and I find that it's probably the most the one that's reported the most. So using a 4 predictor model, I'm going to create this ROC curve, and it's easy to do. You have to install the package PROC. I didn't install the sources from the package that needed compilation, and then of course I have to access the library. The next thing I do is when you call this line, and again, this line is just ROC, your dependent variable has to go there, the dichotomous dependent variable. As long as you call your model, just type that. And actually, you probably should, use this and add legacy axes equal true and do plot equal true. Obviously, you want plot equal true because you want to see your plot. So when you do this, you're going to get this graph. Just copy paste it into your document. Now, once you type ROC and call that command, you get something really interesting down here called your AUC, the area under the curve. And you can see that I have reported that right there. Now, turns out this is not impressive. The metric for deciding AUC, we say AUC equal 0.5 is or below is very poor. 0.7 to 0.8 is acceptable, so we are below the acceptable, so we're in the poor accuracy range. 0.8 to 0.9 is excellent, and higher than 0.9 is just you've just ventured into an acceptable, an outstanding model for predicting your dependent variable, in this case be false status. So you're going to be replicating this with another data set, so really just make sure you add the descriptives and then just keep the words the same and just go in and change the values to correspond to the analysis that you're performing. All right, gang, hope this helped.